We're going to start chapter 7 and do 7.1. So the first section is population proportion. So what we'll be looking at, so overview, percent, probability, and proportion. We're going to use statistics to do some inferencing. So we have done a lot of just descriptive statistics. Well, now we're in the part where we're doing some inferences. So our first part of using inferential statistics involving sample data to estimate values for the population, not from, for. So be able to use some information from some sample data to estimate about the population. And then we'll also test claims, which are also called hypotheses, made about a population. The population. So for 7.1, it's all about population proportion. So this is where we use the P and the Q. When you have P as success and Q is failure. And what P and Q are proportions. They're percents, which are written as a decimal. Together, they add to equal 1. So P is going to be our population proportion. And P with, it almost looks like it has a hat. We're going to call this P hat. Let's put a dash there. It's going to be our point estimator or point estimate. It's found by doing how many you have over N, which is your total sample. And then we also have Q hat, which is the complement to P hat. With proportions, we're going to estimate those as decimals. So when working with a percentage, express it in decimal form. So you'll just need to pay attention to how many decimal places you're supposed to round to. Our point estimate, which is our P hat, is going to be our single value used to estimate a population parameter. So parameter is mean, proportion. So for this section, we're looking at population proportion. How much of the proportion of the population is in this section that we're looking at. If we want to estimate a population proportion with a single value, the best estimate is P hat. So remember, P hat is found by doing X over N. So equals X over N. We use P hat because it's unbiased. and it's consistent. So example 1, the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them knew what Twitter was. Based on that result, find the point estimate of the proportion of all adults who know what Twitter is. They actually just gave it to us. P hat is that proportion that know what Twitter is. So it's 0.85. Example 2. Touch therapists participated in 280 trials of their ability to sense a human energy field, in which in each trial a touch therapist was asked to identify which hand was just below the hand of Emily Rosa. Among the 208 trials, there were 123 correct identification. The success rate, P hat, was 123 out of 280, which was 0.44. Using these test results, find the best point estimate of the proportion of all correct selections that would be made if all touch therapists were tested. They gave it to us, P hat. That is our point estimate. So a point estimate is great to find a proportion to estimate for the rest of the population. But the problem is, it doesn't reveal how close the estimate is to the actual population proportion. So what we are going to learn about is confidence intervals. And that's going to give us a sense of how good that estimate is. So is that estimate, are we 95% confident? Are we 90% confident? Are we 99% confident? The more confident we are, the better of an estimator it is. So our confidence interval is a range or interval of values used to estimate the true value of a population parameter. So an interval will be a range of values. So instead of saying 0.44, an example would be, let's say 0.35 to, let's say 0.52 or something like that. That would be an example where your point estimate is in between. That's just a random example I came up with. So it's between those two values. We're going to abbreviate confidence interval with just CI. In order to do your confidence interval, you need to decide what kind of confidence level you want to use. 0.95 or 95% is the most common. You could do 0.8, 0.75, 75%. That's how confident you would be. So it gives the success rate of the procedure used to construct the confidence interval and is expressed as a probability or an area 1 minus alpha, lowercase Greek alpha, where alpha is a complement of the confidence interval. Confidence level is going to be CL. This is the probability. Remember, probability and area are directly related. 1 minus alpha. That the confidence interval actually does contain population parameter. Assuming the estimation process is repeated a lot. So that's what our confidence level is going to be. How confident are you, or is the interval, that the actual population parameter falls in that interval? Also called the degree of confidence or confidence coefficient. The most common are 90 with alpha at 10, 95% with alpha at 0.05, and 99% with alpha at 0.01. 95% is most common because it gives a good balance between precision, the width of the confidence interval, and reliability expressed by the confidence level. So let's talk about what 95% confidence level means. So let's do our normal curve. The 95% confidence means that the area, the interval, think about the low point and the high point, and the population parameter, whatever that is, let's say p hat, falls in that area. So this area is 0.95. So then here would be what's left, because this whole thing has to make 100%. So if this is 0.95, we have 0.05 left. So each side would be 0.05 divided by 2. So that'd be 0.025 on each side. So that's in 2 tails. So that's going to become important in a little bit whenever we use that t-distribution chart. So let's think about an 80% confidence level. So let's think about how these are going to be the same, but then how they're going to be different. So if this area is 0.95, I'd want to make this one 0.80. So is that going to be wider or narrower? If the area is smaller. Yeah, it's going to be more narrow. So let's say it's more like that. With P in the middle. Or P hat. So then on both sides, in your 2 tails, you have 0.20. But you got to cut it up into 2s. So this would be 0.10. And this would be 0.10 in your 2 tails. So together it's 0.2 in 2 tails. In 1 tail it's 0.10. So this is wider. Bigger area means it's wider. Example 1, based on the sample data of 1,007 adults who were polled, 85% knew what Twitter was. We're going to use the confidence interval of 95% to estimate that the population proportion is 0.825 to 0.8725. So what this means is our p hat is the 0.85. That came from the proportion. And we want to look at our confidence level of being 95%, so 0.95. So 95% confidence interval gives us that P falls between 0.825 and 0.872. So the correct interpretation. So it's not all about just finding the answer. You have to be able to interpret it as well. So this is our interpretation. We are 95% confident that the interval from 0.828 to 0.872 actually does contain the true population proportion. P. The second interpretation, if we were to select many different random samples of the sample size of 1,007 in 1,007. And from that, construct intervals. 95% of them would contain the actual P. Where P is your population proportion. The incorrect way of describing this. This is where a lot of people want to go with it, but these are the correct interpretations. Incorrect would be there is a 95% chance that the true P will fall between that interval, 0.828 and 0.872. So that is incorrect. We're not going to worry about that one. There are two correct ways to interpret it and then one incorrect way. So let's interpret this first example. Based on the sample data, 280 trials of touch therapists, with 44% of the trials resulting in correct identification of the hand that was selected, 95% confidence interval estimate of population proportion is 0.381 to 0.497. So the correct interpretation is, the way that you can do it is use this and rewrite it. So we have a confidence interval of 95%. So start it out the same way. We are 95% confident that the interval from so let's fill in the interval. They've given it to us here, 0.381 to 0.497. Actually does contain the true population proportion. P. The incorrect interpretation is there's a 95% chance that the true value will fall between those. Instead, it's we are 95% confident that the interval actually does contain the population proportion. P is fixed, so the confident interval limits either contain P or don't contain P. We're going to skip that example. Confidence levels tell us the process that we are using will, in the long run, result in confidence interval levels that contain the true population proportion 95% of the time. So this makes it a little bit more concrete, I guess. Let's look at the interval of this. The interval here, that's supposed to say P, I believe. Yeah, it's hard to see. That says P. So we're saying that P is 0.9. And we have intervals of samples of data. So look at these intervals. The intervals are drawn with a line. So you have your lower and your upper, and in between them, you draw a line, making it an interval. There's only one out of those 20 that don't contain the true P. See how all of these have the P in the interval? It's on the line that's drawn right there. All but one. This one, the interval does not contain the true P. So 19 out of 20 is, what is a percent? Isn't it 0.95? So we are 95% confident that the interval from, what is it? I don't know what it'll be. Does it give us, oh, it's right here. There's the interval. 0.828 to 0.727. So it's so hard to tell. 828 to 872 actually does contain the true population proportion. So all but one. So this one is actually a little different. It gives you 0.90. So it's looking at a different population parameter. All right. Let's look at critical values. Critical values are your Z. So Z alpha, it's the Z score with an area of alpha to its right. So the critical values are the cutoff values that define regions on the normal curve. So your Z-scores. You're going to have an upper and a lower Z-score. So we're still going to use the Z-score table. So we're going to look at Z is 0, so that's our normal distribution. Standard deviation is 1. We are going to denote the area of each shaded tail by alpha over 2. So remember, alpha is found by doing the 1 minus the 95, or whatever your area is, the probability. So we'll look at the example. So it says find the critical value corresponding to a 95% confidence level. So let's draw our normal curve. We want 0.95 as the area. So we need to find out what alpha is and then what alpha over 2 is. So our confidence level on this one is 0.95. So alpha is found by doing 1 minus the 0.95, whatever your confidence level is. So that's 0.05. And we want to find alpha over 2 so that we can find the area of the tails. So that'd be 0.05 divided by 2. 0.025. So we can look at our z-score. So we want this area right here to be 0.025 and this area right here to be 0.025. So we're wanting to find the area. We want to find the z-score with an area of those two. So these are symmetrical because you have 0 in the middle. So this one will be negative, this one will be positive. So if we look for 0.025, 0.025, we can find right here. So I'm looking at to the left, negative z-scores, because that's an easier one. Oh, it's the old one. It's the z-score. We're not using the t-chart yet. So get out the one from chapter 6. I'll have to get it back. Yeah.
Did I really?
Well, somebody did.
I think that's mine. You have that name on the corner? Yeah.
Yes.
Where you get that from?
Yeah.
No, but I just want to go to my car and need to get that in.
All right, so we look for 0.025, 0.025. So it's right here, negative 1.96. So our z alpha over 2. So this one, the negative one, is negative 1.96. And then the positive one is positive 1.96. And what our table actually gives it actually gives it to us. So look down here at the bottom. On the positive z-score side, look at the bottom. It will actually give us some of the common critical values. So that's going to be helpful. So circle that. Common critical value. So z alpha over 2. That's what it is. Z alpha over 2. So 95% confidence level, our critical value is 1.96. So Z alpha over 2 for a 95% confidence level is 1.96. So other common ones, 0.90 and 0.99 are on there as well. So that's what our next page actually asks us. So confidence intervals, or confidence level, and then our critical value. So our confidence level is 90%. So then our alpha is 1 minus our confidence level. So in this case, 90% would be 1 minus 90.9 would be 0.10. Then 0.95, 0.05, and 99.01. So our critical value for each of these, like I was saying, is already on here. So that really is helpful. Go ahead and copy those over. For 90% confidence level is 1.645. 95 is 1.96. 99 is 2.575. So an example of one of the problems on the homework is find Z alpha over 2 for a 72% confidence level. So the best thing to do to start out is to draw it. That's a funky looking one. So we have 0.72. So it's not very wide. I kind of made mine wide, but the area is 0.72. So we need to find what's the area in each one of the tails. So we would need to subtract from 1 to find alpha. So alpha is 1 minus 0.72, which gives us 0.28. And then for each of the tails is alpha over 2. So 0.28 over 2. 0.14. So we would want to look at our negative score and look for 0.14 in our area. So look in the area, 0.1401. That's probably the closest one. So when we're using the table, we're going to find our closest one. So that looks like it's at negative 1.08. So Z alpha over 2 is negative 1.08. Well, it's negative and positive. So let's just put positive. So this one's going to be negative 1.08, and this Z-score is going to be positive 1.08. So our critical value is 1.08. So we're going to use all of these things like critical value, P, Q, and N to find our margin of error and then also find our confidence interval. So the margin of error is going to be max likely difference. So maximum likely difference between P hat and true P. And it's denoted by E, which is margin of error. Also called the max error of estimate. Here's our formula. We're going to plug in our formula to find E. So the Z alpha over 2, that's our critical value. P hat is our sample proportion. Q hat is the complement, and then N is your number of trials. After you find your margin of error, you add it to your p hat and then subtract it from your p hat. And that gives you your two values for your interval, which can also be written as a inequality. So look at this formula. P hat minus E is less than P is less than P hat plus E, where E, we just looked at that formula. We can also write it with parentheses around it as an interval, or P hat plus or minus E. We're going to round it to 3 significant digits. So let's do our example for that. These are the steps. Let's go ahead and just go step by step on this one example. So we have the same example we've been talking about with 1,007 is in.
Teachers, I'm sorry for this interruption, but any senior that is needing to turn in.
Okay, so N is 1,007. P hat is our proportion that we're given, so 0.85. Q hat is going to be the complement of 0.85, so 0.15. And we want a confidence level of 90%. So our critical value is going to be the next thing we find. Remember we wrote this down for a 90% confidence level? It's on the last page, but it's also right here. Okay, we have everything we need. So all we have to do is plug it into the formula. So we need to find our margin of error. Here's the formula. Which is above it. So I'm going to write it down and then we'll put it in our calculator. So our critical value, that's our Z alpha over 2. So it's going to be 1.645 times, do our P hat, so 0.85, times our Q hat, 0.15, over N, 1,007. So plug it into our calculator. And just make sure you put it in correctly with your square root of the whole fraction. I'm going to go ahead and just show y'all what I got. We're going to round to 3 significant digits, remember? So 0.0185. So that is our margin of error. So to get our confidence interval, we are going to do P hat plus and minus our margin of error. And that'll get our two values for our confidence level. So 0.85 plus and minus 0.0185. So 0.85 minus to get our first one. Oh, sorry, that's glared pretty bad. So the first value, 832. And then I'm going to go back up here and change that to a plus 0.869. So you can write it as an interval like that, and you can also write it as an inequality. 0.832 is less than P is less than 0.896. And I'm going to show you what that means. So you can look back at our interpretation. So we, or 1, has 90% confidence that the interval from 0.832 and 0.869 actually does contain the true value of the population proportion. So that is it for 7.1.